Great, thank you. Yeah, and first let me thank the organizers for putting this together. And yeah, I'm really happy we were able to do this at least partly in person. It's great to be here for my first trip since March 2020. So yeah, I wanted to talk about the classification problem for C-star algebras. But I also want to point out and actually throughout this, I'll point out there's a lot of analogies between von Neumann algebra theory classification and C-star algebra theory classification. We'll start here with the von Neumann algebra version, which is much cleaner. So separably acting injective factors. So Jesse defined some of this last time. A factor is a von Neumann algebra trivial center. Separably acting just means it's defined on a separable Hilbert space. Injective, Jesse alluded to it. It's the right notion of amenability for von Neumann algebras, but it means there's a norm one projection from B of H onto the algebra. So we have a complete description of these algebras, and they're classified by their type, which is says something about the structure of traces on the algebra, and what's called the flow of weights. I won't say too much about what those actually mean, but we have a complete list of all these examples. And there's been this push for a long time to find producing a C-star algebraic version of this. So this has been many people over several decades that let's say separable. So a von Neumann algebra version, C-star algebra version of a factor would be a simple C-star algebra. So no two-sided ideals. The C-star amenability condition is nuclearity. And so the conjecture was starting in the probably 89, 90, around there, that separable simple nuclear C-star algebras would be classified by their traces in K-theory. Just some of the type is encoding tracial data, and then extra topological data will show up in the C-star algebra setting encoded in K-theory. There's turned out to be two other obstructions needed, which are Z-stable and satisfy what's called the universal coefficient theorem. These are classified by K-theory traces. It's always hard to put a year on this. It's just probably started around 89 and is in some sense still going. And it's been steady progress almost the whole way through over the last 30 years now. The unital version is done. The unital version was about 2015 with something in place, finite nuclear dimension in place of Z-stability, but it turned out to be equivalent. The non-unital version is still being written up. There's now, I think, 2 proofs in non-unital version. One of me and my co-authors, and the other of Gong and New. Okay. I'll mention we'll try to talk something about how one proves this over the series of talks. First, I'll say more about what it means. But when it comes to actually proving this, I'm going to add some assumptions. The algebras will have units. They'll have unique trace. And in particular, they should point out with the non-reference here, when there's no traces, this was done by Kirchberg and Phillips in the early 90s. It's the almost everything that's been happening is in the setting where there's at least one trace. And that Z stability is going to be replaced with UHF stability. I'll come back to that too. Okay. Okay. Before I say too much what these things mean, let me just give some examples. So start in the von Neumann algebra setting. So actually in both settings, some of the main sources of examples of operator algebras come from dynamics. Let's take X mu to be a standard probability space. So for instance, let's say X is a compact metrizable space and mu is a Borel probability measure on X. G group, which I'll always assume to be countably infinite. And in this setting, I want it to be amenable. And action, which is a measure preserving action. And it's going to be the same conditions as was in Jesse's talk yesterday. I want it to be a factor, and the magic conditions for that are that it should be essentially free. So almost every point in X has trivial stabilizer and ergodic. So any subset of X which is fixed by the action, or any subset which is G invariant, has measure 0 or measure 1. So it's essentially empty or the whole space. So this, I'll put a bar there because I'm going to have C-star algebra cross products too. But this cross product algebra, in the sense it was fine yesterday, you have this von Neumann algebra encoding the dynamics. It'll be a factor because of the freeness and ergodicity. It'll be the injectivity will come from the amenability. So it is actually an injective factor. It always has type 2-1. So this is actually independent of not only it's independent of the action, the group, and the space you're acting on. Which is really just miraculous. There's a lot of group actions out there, and somehow they all collapse when you pass this von Neumann algebra. In the amenable setting, without amenability, you can often recover very much about the action from the von Neumann algebra. So the second one, just to show you how bad this can fail in the C-star algebra setting. Take consider an action of the integers on the circle by rotation. Where say it's an irrational number. So when you act it by an irrational number, the action's aperiodic. That's yeah. You start moving a point by something like 1 radian, it'll never end up back. It'll fill out this dense set in the circle. But So when you take the cross product by this action, which is defined exactly as in the von Neumann algebra setting, just with a norm closure instead of a straw and operator topology closure. And the classification of these things long predates this theorem. It's late 70s, early 80s, but these algebras are covered by the theorem. They are simple nuclear, separable, Z-stable, and satisfy UCT. But it turns out they're almost never isomorphic. There's a plus or minus there. So the only way they're isomorphic is if the theta is either different by an integer or by a sign. So if you think about the backwards direction, I mean, if you're rotating by 2 pi theta radians, if theta 1 and theta 2 differ by the integer, it's the same rotation. It's exactly the same action, so it's going to be the same cross product. If they differ by a sign, the isomorphism is just flipping the circle over the real axis. I mean, if they differ by a sign, you're either rotating to the left or to the right, rotating in the positive or negative direction. You can conjugate one to another by flipping the circle over. The forward direction, deciding when these, finding like reasonably computable isomorphism invariance for this took quite a long time. There's what ends up happening is A theta has a unique trace, which for me, trace always means a tracial state. So it has unique trace. The point is it's well, the traces on C of X are probability measures. If you have a measure which is a variant under the action, it'll extend to a trace. So this is just given by the Lebesgue measure on the circle. It's rotation invariance, so it'll give you a trace on the algebra. Explicitly, I guess, if you took, so a dense set of elements in here are finite sums, continuous functions times group elements. So you can write it, say, this way, where U is the generator for the integers. What you do is you pick off the 0th coefficients and integrate over the circle, and you can compute that's a trace. Yeah, computing as a trace does in the end comes down to just the measure being rotation invariance, Lebesgue measure being rotation invariance. So it's a unique trace. Takes a little bit more work. There's no other rotation invariant measure on the circle, but in principle, something weird could happen with the group. It doesn't. Right. Okay, and so where the actual isomorphism invariance is, what was done actually in terms of the K0 group, which I'm trying to avoid for at least for a moment longer. So I'll write it in so if you look at the set of all trace of P, where P in A theta is a projection, but it's not at all obvious this algebra has projections. There's one of the big pieces in showing this direction was Rieffel's result that, well, if you assume theta's between 0 and 1, this actually has a projection of trace theta. But it turned out all the projections, you can give a complete description of what the possible traces are. They're all real numbers of the form integer plus integer times theta, which happen to lie in the interval. And you can check pretty quickly if you have this set, you can recover theta from this set up to an integer multiple and a sign. That the uniqueness of the trace implies if these are isomorphic, then they give the same sets here, and then a little bit of arithmetic tells you the relation between theta 1 and theta 2. It's just a subset of real numbers, nothing fancy. So even for actions which look in C-star algebra setting, where even for actions which look incredibly similar, they're often not. They often give very different cross products in some sense, or at least different cross products. Right. Okay. And a third example, it's much more general. I won't be able to compute things as nicely, but just give you an idea of that there are a lot of things in this class. Take X to be a compact metrizable space. G, countably infinite still, amenable group. Take an action which is, well, instead of essentially free, it's going to be topologically free, which means a dense set of points have trivial stabilizer. And instead of ergodic, the right word becomes minimal. This was essentially no measurable invariant subsets. Minimal is going to be no closed invariant sets, except the empty set in the whole thing. And you can almost get there, not quite. This will be, well, separable, of course. Nuclear will again come from amenability of the group. What else did I say? Simple, that comes from the action being free and minimal. UCT is a very deep result of 2. Yeah, Z stability is the missing condition. And in fact, I think in general, for applications of the theorem right now, Z stability is usually the roadblock. So it's not true in general. And actually, it's not true in general here. There's actions of the integers on spaces where, like I think a Hilbert cube or something like that, which are not Z-stable. This was a Gio and Kerr. But if you add some conditions, so if the space is finite dimensional, I mean, probably the first result, Tom's and Vinter showed for integer actions, you'll get Z-stability under these other assumptions. This has been slowly built up to more and more general classes of groups. It's known now, for instance, if G has sub-exponential growth, or very recently, elementary amenable. This was Kerr and Szabo. This was the elementary amenable one is David's result from, I think it was posted just about a month ago, or last month. But then the cross product is what's that? Oh, I'm sorry. Was there? I should have written that down. Who is your co-author on that, David? Oh, sorry. Yeah, I'm really sorry. I been slapped with what was your last name? Okay. Let me just. Yeah, I'm sorry. I'm not gonna try to spell that. Okay. So pay more attention to my notes. Okay. Yeah. But anyway, for an enormously large class of groups now, and finite dimensionality of space probably isn't such a big restriction. We can actually verify the stability. We means other people, not me, but. Yeah. Okay. Right. So I want to say more about, I think, next what this invariance is. That's actually classifying the algebras. So I said it's so it's K-theory and traces, and I'll give it just a very brief intro to K-theory here. So this first part is K0, which was sort of implicit in the irrational rotation obstruction. So you start with, let's say, a unital C-star algebra. So look at Pn of A as all projections. Projections large and by matrices, and you can nest these by sending embed each into the upper left-hand corner of the next and take their union. Right. So you're looking at projections of arbitrarily large size. And the reason you want to amplify like this is so you can get an additive structure. So stick them on the diagonal of this larger matrix algebra, which I can do because I'm allowing myself arbitrarily large matrices. Then what you want is this essentially gives you some kind of addition, which you'd want to turn into build a group out of, to make it associative and commutative and things like that. You need, there's the equivalence relation in here. Right, P equivalent to Q, this is going to be Murray von Neumann equivalence. If there's a V, so partial isometry whose range is V and source is Q. If you're on if A was B of H, this is just range of P and range of Q are isomorphic, which is P and Q have the same dimension. Okay, then P of A mod this equivalence relation is an abelian monoid under direct sum. The zero projection is the unit. And you can take the group this generates, just look at formal differences. And that's a group called K0 of A. You should think of it, K0 of A somehow acts as if you have a projection P, you can define the rank of P and have a number, it's an element of this K0 group. For the complex numbers, K0 of the complex numbers is the integers by sending a projection to its rank. Right, so that's going to be part of the invariance. There's another group, K1. Well, you can play the same trick with, or play the same game with unitaries. Look at the m by n unitaries inside the m plus 1 by m plus 1 unitaries, where you just stick a 1 on the last diagonal entry to make it unitary. This one has a quicker definition. It's all unitaries modulo the path component of the identity. So two unitaries are considered the same in this group if there's a continuous path from one to the other. So this is an abelian group. I mean, it's not to show that's a normal subgroup, so the quotient is a group. Abelian is actually, there's actually a trick too. It's, if I didn't put matrices there, it's actually false in general. So unitary group by the path component of the identity does not have to be commutative, but one direct sum u and u direct sum 1 are always in the same path component, and you can use that to, you know, if you're trying to multiply u by v, you stick in that extra matrix and move one of them to the second entry, and you know, u1 will commute with 1v, and then you put it back together. Right. Okay. And they're not completely unrelated. They're if you have an ideal, so if you have an extension of C-star algebras like this, they fit the K-theory groups. Let's just go over here. Induces a exact sequence of abelian groups. Which is one of your most powerful computational tools when it comes to computing these. It's, I mean, it's like with almost any homology theory, the definition you write down is usually useless when you actually want to compute something. But you prove things like homotopy invariance and existence of long exact sequences, and you have a chance of actually doing computations. I'm cheating a bit. There is also a definition for non-unital algebras. That, you know, basically, if in the non-unital case, you define your way to make this statement true by adding units and playing around with it. You know. But okay. So, and time. Okay, so the final main piece of the invariant, you have the K0 group, a K1 group, and traces, which are all tracial states. So, oops. So that's always a compact, convex subset of a dual. Right. And actually, I can do this. Is this good? I don't know how I can put this up without blocking the screen here. Is that good still? All right. All right. So you have the K0 group, the K1 group, traces, and then there's just a little bit of extra data, but let's just, so the Elliott invariance of A so you have the K0 group, but also a special element. So K0 is built out of projections. The unit is a projection in the algebra. You want to keep track of that element. That's what will allow you to distinguish between A and the 2x2 matrices over A. You have the abelian group K1, traces. In the final data, it's actually also sort of implicitly showed up. What distinguishes the rotation algebra is, in fact, it's abstract groups. Those rotation algebras, their K1 is always Z squared and their K0 is always Z squared. But the K theory, and they always have unique trace. But this data alone won't tell the rotation algebras apart. But what's special is how the trace map the projections into the real numbers. The range of the trace is this subset of the reals that determined them. In general, what you have is a pairing that, given a trace and a projection, you can evaluate and get a real number. And that's the extra piece of data you need. So that 5-tuple. So in isomorphism, it's then the obvious thing. You have an isomorphism K0 to K0, K1 to K1, T to T, so that the unit got mapped to the unit in K0, and the pairing is compatible with the isomorphisms in the obvious way. So that classification theorem, it's for A and B is in the theorem, they're isomorphic if and only if their Elliott invariants are isomorphic. Yeah, I should mention that. Yeah, often one includes which is, well, the projections modulo the equivalence relation viewed as a subset of K0 plus. That's not actually a subset, but I mean the image of that map into the group. So that's some positive comb, which gives you an order on K0. It's not actually needed though. It's included for historical reasons, but for A, as in theorem, the classification theorem, or even under slightly less conditions, you can recover this as all the K0 elements, which are positive on every trace. Together with 0. It's coming from simplicity and Z stability, and I guess nuclear, so quasi-traces are traces. And yeah, usually, I mean, historically, when things were real rank 0, the traces weren't part of it at all, or part of the invariance in K0 plus was, but yeah, it turns out it's not actually needed if you include the traces in this pairing, and it's well, the new proof of the theorem that this doesn't make any use of the positivity in the proof. Yeah.
Could you just clarify? You said that when the Elliott invariants are the same, you get an isomorphism of the C-star algebras. What do you mean by the Elliott invariants being the same?
Yeah, so the isomorphism of the invariants, you have a isomorphism K0A to K0B that takes the unit to the unit, an isomorphism from K1 of A to K1 of B. Well, traces, it's usually in the other way, and written as isomorphism from traces on B to traces on A, because contravariant. And then the pairing, everything fits the way it's supposed to. If you relabel a trace on A with the corresponding one on B and the K0 element of A with the corresponding one for B, the pairings on A matches the pairing on B. Yeah. Okay. So this, it looks like a lot of data. It actually is, in practice, relatively computable. K0 and K1 are infinitely generated abelian groups typically that, you can't expect a really nice formula because we don't even have nice lists of all abelian groups or of all countable abelian groups. But if you say specialized to cross products, there's this whole industry, that's the Baum-Kahn conjecture. So it's a Baum-Kahn conjecture, which is true for amenable groups, that would in principle, let you, what it does is it computes the K theory of the cross product in terms of some topological data, the K homology of some appropriate space built out of the action, but you have some hope of at least getting partial information out of, by topological methods. In the case of cross products, the traces are going to come from invariant measures, G-invariant measures on the space X. And the pairing can also be a pairing might be it's probably a little bit hard. I don't actually know how to write down off the top of my head, but it's I think the pairing is somehow can be interpreted dynamically as well, as I remember. But it's so in practice, this group is reasonably computable, or this Elliott invariant is relatively computable. Right. The one last thing I wanted to try to say something about here was the assumption that usually gets brushed over entirely, this universal coefficient theorem condition. What that actually means. In practice, it's relatively mild. It's not clear if it's actually, it might be automatic, for all we know. But where it's coming from is a computability condition on K theory. So for C-star algebras A and B, say separable, can define an abelian group often B is assumed to be sigma unital, or so it's countable approximate unit. That's actually not needed if you're careful with everything. And I'm not going to be careful enough with anything for it to matter anyway. But if you take, you can get by without conditions on B. But you can define this abelian group, which consists of certain generalized homomorphisms. One of the main problems with difficulties in proving the isomorphism theorems is, if you're trying to show A is isomorphic to B, one way or another, you eventually have to write down an isomorphism. And there's typically very few homomorphisms between non-commutative algebras in general. Even there's often very few maps between them. And even whereas when you do have maps, there's not any reasonable structure on the set of maps. You can't add them, or no convex structure or anything of the sort. So what this somehow does is, by enlarging your definition of morphism a bit, gives you an algebraic structure on the set of morphisms. You have that richer structure to work with. For people that do von Neumann algebras, it's the same reason people talk about correspondences between von Neumann algebras and as opposed to just normal star homomorphisms. But so one way of defining this is to, instead of looking at morphisms just from A to B, well, first thing you could do is look at morphisms A to matrices over B and add them by direct sum, like you did with K0. That turns out still not to be enough because there's just not enough morphisms between A and matrices over B. That what you can do instead is look at morphisms into some larger C-star algebra E, a pair of them, which contain B as an ideal, or B tensor that compacts as an ideal. So that their difference point-wise lands in B tensor that compacts. I mean, this is supposed to play the role of phi minus psi in this group. And you take this modulo some suitable notion of homotopy. A homotopy would be a generalized morphism from A to C of 0, 1 tensor B, which when you evaluate at the endpoints restricts to the given two maps. Right. So first thing to note is there actually is, there won't be many homomorphisms from A to B tensor that compacts in general, but it turns out there will be several of these generalized morphisms. I mean, well, you could be in the case where A has a lot of projections and B doesn't have any, then you have no chance of building a morphism at all. But yeah. So if you take well, you have about, look at the bounded operators of the Hilbert space. I can represent that as multipliers on B tensored with the tensor with the compacts, where you just act, an operator acts on the compact parts and leaves B alone. And this thing contains B tensor that compacts as an ideal. I mean, any C, let's say a separable, any C-star algebra is going to represent on this B of H. And so I'll get stake to be some phi. And then I could, conjugate phi by a unitary and B tensor compacts plus scalars to build a psi. So you actually do have many of these generalized homomorphisms. So there's, somehow have enough maps out there to actually start constructing this theory. And so I won't go through what the group structure is entirely, but addition is some form of direct sum using that 2x2 matrix over the compacts as the compacts. Inverse is, well, if you think of it as phi minus psi, the inverse is going to reverse the roles of psi and phi. And 0 is, phi phi for any map phi. 0, 0 would do, for example. But there's also a lot of computational tools for these things. There's a natural composition, which extends composition of homomorphisms. I should point out if phi maps A to B tensor the compacts, you can form morphism, let's say A to B, I can map A into B tensor of the compacts by sticking in the 1-1 entry of the compacts, take the other thing to be 0, and that gives you, you can view as the class of phi in this. So these really do extend your notion of homomorphisms. In that case, I guess E is equal to B tensor compacts. Right. But yeah, there's a composition of these things that generalizes composition in the special case of morphisms. They fit into various 6-term exact sequences in each variable. They're homotopy invariant in each variable and several other things like this. And probably one of the most important properties is, homomorphisms will act on K-theory by sending projections to projections and unitaries to unitaries. These generalized maps also act on K-theory. So this pair phi psi does induce a map from K-theory of A to K-theory of B. And the UCT is a statement about that map. Okay. So I'll end with this. So this, well, C-star algebraists have a bad habit of using the universal coefficient theorem as an adjective, but there is an actual theorem behind this. So I'll start with what I think is viewed as the more natural condition, even though it's not the one you usually see. If you imagine you wanted to compute one of these things, oh yes, write down first. So there's a separable commutative algebra with KK of A something is isomorphic to KK of, call it D, KK of D something. So whenever you stick a B in that, they're isomorphic to functors. So whenever you stick a B in that second variable, they're isomorphic. And you can arrange the isomorphisms in some coherent way over all B's. Well, the point is, if you stick a B in this second variable and let the commutative algebra D vary, this gives you a generalized homology theory on spaces. And you actually have access to a lot of algebraic topology available to compute this thing. So this right-hand side is actually very computable through topological methods, and can we turn it into a problem about not reasonable topological spaces. So if they're isomorphic, you can compute the KK theory of A. And the second part is a computation of Rosenberg and Choquette, which did exactly this, reduced it to the commutative setting and compute there. So it says, first of all, that this map is surjective. The KK to Ham. It's actually usually not an isomorphism, but that has a controlled. The kernel is well understood. This is for all algebras B. The real point to this is if you're trying to prove the classification now, you're going to be given an isomorphism K theory of A to K theory of B. This, with a little bit of work, you can show it lifts to an isomorphism in this KK. So the isomorphism K theory now doesn't come from homomorphisms of algebras, but something not so far away. You actually have some chance of realizing that those K-theoretic maps at the level of C-star algebras, and that realization is unique up to something that you can is relatively computable and that you can control. I'm already over time, but I'll say there's the nuclear algebras you run into in practice usually satisfy this. If you can construct them in any reasonable way from the commutative algebras or finite dimensional algebras, somehow build them up, they will satisfy UCT. There's no nuclear counterexamples. It's been an open problem for ever since basically since '87 is every nuclear algebra in this class, and there's not really great evidence either way at the moment. It's still very much wide open. But okay, I'll stop with that. And
thank you very much for